So anyway, these are those equipotential lines, and everywhere they cross the electric field lines, you can see they cross them at 90 degrees. Same thing here with these circular ones, and each one of those lines represents a different voltage, a different potential difference there. And then the work can be figured out by how much of a voltage difference there is. If you move between equipotential lines or equipotential surfaces, then that times the charge that you just moved is going to give you the amount of work that you had to do to move between those. Okay, and then here, if we remember, all the charge resides on the surface of a conductor. Therefore, all of the field lines coming off of the surface of the conductor are all perpendicular to that surface, and therefore we have an equipotential on the surface of it. And you could even call that one 0 if you wanted, but essentially the surface of a charged conductor is an equipotential surface. And the electric field lines come off perpendicular to it everywhere. And of course, if you have the same amount of charge on something, but it's smaller, then it's going to be, you know, they're all more tightly packed in there, and you have a stronger field close to the surface. And of course, here still, it's stronger field over here where you have where it's sharpest, where you have the smallest radius of curvature there for it. Okay. So more curved means larger electric field around the more curved parts. Here, it's just talking about, y'all probably know this, I know a lot of y'all are biology people, and there's one of those example problems about the heart and having to shock it back into working, right? And so an electrocardiograph, and it just plots electrical activities as it goes through the body. I remember we had you ever hear about the people who get like hit in the chest, not very hard, like playing a sport or something, and then they suddenly like a minute later have a giant heart attack? Never heard of that? Where they'll like get hit in the chest, real simple, and then they like get up and they're fine for a few seconds, and then they just collapse. That's why like every sports now has to have a defibrillator right there at that time. I remember watching I had a guy who came in and they were growing these heart cells, and they were figuring that they'd get them to beat, and they'd beat with very predictable waves of voltage going through them. And he found that if you introduced a jolt into it at the right moment during the beat part, he could get it to start beating irregularly and start to spiral out of control, in which case they would all just stop. And so it was like right along with that, what causes that? If you get hit at that, I mean, it had to be really perfectly timed, and it just caused an extra little wave in there that started propagating and building up, and it just made it all go wild, crazy, and then stop. They could like shut the whole system down if they did it at the right time. It's kind of neat and a little scary, I guess. So here's electrical activity of the brain, okay? And same sort of thing. Now, capacitors. Capacitors are a nice way to store charge. We talked about them a little bit before, but not really how we do it. Here is the simplest capacitor is two conducting plates that are separated from each other. There's an electric field then between them. You pump a bunch of charge onto one of them. It then forces the charge off the other one. So, you know, you attach them to both ends to a battery or something. You throw a bunch of positive charge on one, it repels the positive charges off the other one, you let it go. And so one becomes positive, one becomes negative. Disconnect the battery and you keep them separated. So you have positive charge on one, negative charge on another. This kind of thing is used a lot, like in flashes for pictures, where they give their energy back real fast. It's a real quick jolt. They're used in air conditioners to kickstart the compression, kickstart the fan and everything, get it moving. They're used quite a lot. They can be pretty dangerous, so always be very careful when you're messing with capacitors. And then, of course, you have the surface area and then the separation amount. Capacitance itself, this is essentially the amount of charge per volt we can store on that capacitor. Once you find the capacitance of a capacitor, it doesn't change. So if we apply 2 volts to a capacitor and measure how much charge goes on it, we can then figure out the capacitance. If we then change the amount of voltage applied on there, the capacitance will stay the same. So then we can figure out what the new amount of charge would be. So once you find that capacitance, it's not going to change anymore. It's going to stay what it is. The SI unit for this is a farad, F-A-R-A-D, and it is a coulomb per volt, which should make sense because it's a charge per volt, so it's a coulomb per volt. farads. Most capacitors you come across are going to be in like microfarads and stuff. And you know, mu F. Okay. So charge per volt that we can store on there. More voltage you have, the larger charge you can store on there. Here is a simple capacitor. This is a parallel plate capacitor. This thing is simply just two plates. There's a certain distance between them. Here's the equation that governs it, that tells you what its capacitance is. You can always, after you find that, end up very often setting that equal to charge per volt for solving problems, which I did in some of the example problems, I think 2 of them. Epsilon naught is the permittivity of free space. It basically is a measurement or a constant of proportionality that talks about how strongly the electric field goes through a vacuum. A will be the area of each plate if you're assuming both the plates have the same area. Obviously, the larger the plates, the more charge you can store on there. So it's going to be proportional to the area of the plates. And then it's inversely proportional to the separation between them. The smaller the separation, the larger of an impact the fields from each has on the other. And therefore, you know, the more charges you throw on one side, the more it forces off the other, and the bigger impact they have, and the more charge you can store. So if you want to make a capacitor more powerful, or not more powerful, if you want it to hold more, you make the plates bigger and you make the distance between them really, really small. The last thing you can do is edit this epsilon naught value right here, all right, which we're going to do a little different. We're going to call it a dielectric, but you can essentially put a material in between the plates, a non-conductive material that will amplify the electric field in there and cause a greater charge to be pushed off of one than the other. And, you know, we'll take care of that. You change that epsilon naught. A lot of times you'll see books where they just change it to an epsilon. In this book, we're going to do epsilon naught times the dielectric constant, which is fine either way. And you get that. So your things you can do: change what's in between them, change their area, change how far apart they are. So you might look at a capacitor and it looks like a little cylinder. What they essentially did was took like sheets of like aluminum foil, made them really long, put something between them like saran wrap that's really thin, make like a sandwich out of them and roll them up. And then that's two plates all really close to each other in a small little area and very small distance between them, and you have a dielectric between them. There's more complicated ways they make them now. Includes putting like they'll take like an oxidized something and then put it inside a fluid, and the fluid is one plate and the oxidized material, and so then the separation is only like a few atoms and stuff like that. I think they're even making some that have these polymers, so you have more surface area where they do this, and it has a ton of microscopic holes all in it, so you have a crazy huge surface area, and you have a tiny little separation, which is just the oxidized little part. And so they're getting some crazy new, really, really high capacity capacitors. Okay, this is actually very useful in those things, those stud finders that you put on the wall. I often call them, I think you probably know them by their more normal name, almond finders. Okay, anyway, you got to laugh at my jokes. I make y'all's grades, right? Come on now. So, especially those who had me before, you should know this. But essentially all they do is they take the two plates. Oh, thanks. They take the two plates that are like this and they turn them sideways like that. And then the electric field, so like they put the plates, instead of the plates facing each other like that, they turn the plates sideways like this. And so instead of the electric field just pointing across like this, now the electric field loops over like this, okay? And then what you do is you put it up against the wall. And then of course you have the wall that's in the way and you move it along. And if you come across one of the studs in the wall, it acts like a dielectric. It therefore changes the capacitance of that capacitor because the field is going up, looping up around through it. And therefore there's a change in voltage because more charge can go on there, and it suddenly will then, you know, turn a light on and say, hey, there's a stud here. So to me, that was always one of like the most brilliant and simple inventions. It's so simple, it's so brilliant. I think that's awesome. And they try to do stuff like this too. I've seen where they want to put stuff on you, like to measure your blood sugar and stuff like that, where you could calibrate it somehow. And then I'm not sure how successful that's ever been, but I know people have had that idea where you calibrate it to someone and then, you know, you put something like that on your skin and it measures that kind of a thing and sees what your blood sugar is. So, okay, so that's that basic idea. Here is the dielectric. You put it in the middle, it lines up and it can basically amplify that electric field and therefore increase our capacitance, and we get more charge stored on there. Now, the total charge stored on a capacitor is going to be 0 if we count both plates. So whenever we talk about the charge stored on a capacitor, we really just mean this charge on one of the plates. It's going to be that positive amount on one plate and that negative amount on the other. But in total, it's just neutral. But it's that separation of charge that gives us that. The polarization of the dielectric results in a lower electric field within it. The new field is given by dividing this into this. And so here we go. This is our capacitance, is just K times that other one. So essentially, is that over here? Essentially what that means is we can come back here to this and just add this K in there, add in our dielectric constant. So for whenever we're putting a material in between them, we can do that. Okay. And then the same thing, KV, KQ over V, but you wouldn't put it in both places. Dielectric constants of some different materials here. Just some examples. Air is very close to a vacuum, so we usually, if you're making one in air, you just pretty much treat it like it's one and don't worry about it. That's those two down here. And so it still works, that same equation, when you put the kappa in there, and it still works. All right. So dielectric strengths here. So, okay, that's just some more of them. And then we can look at how much energy we have stored in a capacitor, and it's going to end up being, there's no real reason to memorize these other two. So if I look at this one, it's U equals 1/2. This is the one I always remember, is 1/2 CV squared. And if I were to come along and say like capacitance equals charge per volt, I can take that and I can substitute out for that C there, and I'd end up with 1/2 Q over V times V squared, which cancels those, and I end up with 1/2 QV, so that gets me that one right back. And then you can also do the same thing to get rid of voltage, and you'll end up with this one down here, 1/2 Q squared over C. So really they're all three the same equation, just combined with the definition here, what our definition is of capacitance. So if I were you, I would remember one of them and then just use the idea of capacitance as charge per volt to then come up with any other ones. So it just really depends on what you're given in the problem and how you want to go about solving it. But essentially, you only need one of them, is what I'm trying to get at. For some reason, that's the one that's always stuck in my head. Okay, probably because you can derive it, but anyway. Electrical energy stored in a capacitor can be put to a number of uses. Like I was saying earlier, camera flash, defibrillator, that's in one of the problems, that's one of the example problems. You have to be very careful with them because they are not current regulated. So even if a capacitor doesn't have 100,000 volts on it, like a stun gun or something would, it can kill you because it doesn't have a limited amount of charge. It can just pump it all through you at once really fast. So they are very dangerous. And the weird thing is capacitors, if you just unhook a capacitor and leave it out for a long time, they have a really strange habit of charging themselves. So anytime you ever go to pick up a capacitor, the first thing you're supposed to do is discharge it with something. Like a lot of people will use like a screwdriver or something where they're holding the plastic or rubber handle and they'll touch the two things together. I don't know. I don't want my hand that close to it if it is a big capacitor and it sparks off, but I've seen people do that and they'll just touch the two terminals together with a piece of metal. And I'm like, oh my gosh, don't do that. Make me nervous. But I guess that's better than grabbing it with your hand and getting totally shocked with it. But yeah. And I think that's one of the things you have to do. Anybody ever work on computers? Build computers? So like, what's one of the things you're supposed to do after you turn off your computer before you open it up? You unplug it and you do what? At least it used to be. I haven't done that in so long. You used to then, after you unplugged it and disconnected from it, you used to were supposed to hit the power button again to discharge the capacitor in it that was used to jumpstart it. So you didn't end up shocking something and breaking something inside it. Huh? Maybe it's not that way anymore. Who knows? It's been years since I've done stuff like that. But anyway, if you divide the energy stored by the volume of the capacitor, we can find the energy per unit volume. And so this is like an electrical energy density here we can have. And you get that right there if you ever need to know it. So you basically can figure out how much energy, you know, per size of a capacitor you can store in there. Okay. And then that's about, the page going to turn? There we go. Yeah. All right. So that's it for capacitors. Just remember, when you change, change voltage and stuff like that, the capacitance stays the same unless you physically alter it. Like if you move the plates closer or further away or add a dielectric between it, like in the stud finder. You know what else is a big capacitor? Those, those plasma balls that you touch them and then it all goes to your hand. You ever seen those? That's a giant capacitor. A little ball in the middle is a capacitor. The bottom of it is the other plate. And so the electric fields go out around like that. And they stretch out around this way. And that's what you see in there. You see the gas getting ionized along those field lines that are going out, like out towards the outer part of the desk, and then they loop back around to the bottom. And if you touch the glass, you're essentially like a dielectric there. You increase it in that one spot, and then it looks like it's all coming to your hand as the gas along that stronger field now polarizes. So anyway, any questions from me? This is, we didn't really have much left to do. So the rest of the time, what questions? What can I still go over again? What can we debate? What can we look at? Yeah. Why does it? Yeah. Saying you want to look at this picture here? It's going to help channel more of that charge across it, was my understanding. So does it have to be like denser than the the way I always thought of it is that it helps, essentially it just helps guide the effect of one of them further on to the other. So like if you see here, this positive was right here. And so or let's look over here. We see we have this positive and we have this big of a distance between them, right? But if you look here where the dielectric is, look how close the first positive and negative charge are to each other. It's kind of like it guides that electric field across it a little bit. It was the way I always viewed it. If that makes sense to you. It's not something that's going to totally, polarize, but it's going to line itself up in such a way. I don't think you'd want to put an electrically charged thing in between it because most likely it's going to come in contact with those plates. And so that's going to redistribute charge across. And if it's a conductor, then it's just always going to short it. So I can't say I've ever witnessed the situation where we took a capacitor and put something metal between it. But no, that piece in the middle still stays neutral. It's not gaining or losing charge. It's just aligning up. What else can we look at? Are we feeling any better about this idea of voltage from last class to now, or no? At least one person is? 2 people? 3 people? Kind of-ish? 3.5 people then, I guess? Go up to 4 now, because we have 2 half-ishes. Man, I expected a lot more questions from y'all. Did y'all see where I posted the practice problems up? Has anybody watched that yet? No? Okay. Do you want me to look at the practice problems now? Go through them now? We can see how many we can get through. Okay, yeah, there's 3 copies there. This complete one, I believe, is the one that has them all done. I worked out some of them while I was there, and then another time I was working and I had to take a break because we got a new puppy. And so I had to take the thing out. And so while I was sitting outside waiting on it to actually go to the bathroom, I grabbed out my phone and opened it up and started writing, and then realized, no, this isn't going to back up like that. And it just made a separate copy instead of the copy that like the GoodNotes app here was using. And so then I tried to replace it with it by importing in the GoodNotes, but then it just made another backup and didn't back up that one. And anyway, that should be the good one. So has anybody looked at any of these in particular that you want me to start off with, or? Oh, what was that? I missed it. Was she laughing at me because of my technology issue? Oh, the dog? Ha 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 ha. Yeah. Oh yeah. It's not my favorite dog. My daughters picked this one out. It's mutt. Some mutt dog they wanted to rescue. Medium, I guess. 50 or 60 pounds. I know that its mother was hit by a car, and so, you know. And I know that I like my other dog more. All right. So you want me to go over this one? Just start here or what? Okay. So a uniform electric field is established by connecting the plates of a parallel plate capacitor to a 12-volt battery. If the plates are separated by 0.75 centimeters, what is the magnitude of the electric field in the capacitor? So voltage is E times D. They only ask us for magnitude, so I'm not worried about it being negative E times D. So E is voltage divided by distance. The voltage is 12 volts. The distance between the plates is 0.75 centimeters, which is 0.75 times 10 to the negative 2. And so I just plug those in, 1600 volts per meter. Don't overthink these, but also whatever you do, don't underthink them. Think about them the just right amount and you'll be good. No, I mean, a lot of these are deceptively simple. Like you look at this and you're like, oh my gosh, how can I figure that out? But it's really like, just do that. So there's not a ton of work on a lot of these. That's the whole point of voltage, right? If you can get it understood, it makes doing this a lot easier because it's scalars. They're easy to work with. So there's not nearly as much vector stuff to do. The next chart says a charge of 6.24 microcoulomb moves from the positive plate to the negative plate. Find the change in electric potential energy for this charge. So I just went with I just did the magnitude of it here to start with, because I tend to do that and then think it through, I guess, the other way. So the change in potential energy is just voltage times charge, because remember, voltage is potential energy per charge. And so it's just voltage times charge. And so the voltage across it is 12 volts, and the charge that moved through that 12 volts is 6.24 microcoulombs. You multiply those together, and you get 7.5 times 10 to the negative 5th joules. Now, is this an increase in potential energy or a decrease? Without reading what I wrote there. Right, it's a positive charge going the direction it would want to go, right? The positive charge would want to leave that positive plate and go to the negative plate. It's going the direction it wants to go. Therefore, that is a decrease. And so I just went ahead and wrote, all right, therefore a decrease, put the negative in there, and I got it. Negative 7.5 times 10 to the negative 5th joules. Any questions on that one? No, and that's how you would like hook up a capacitor to charge it, where I hook that, it's a little picture of a battery is what that is, that 12 volts, which we'll learn when we do circuits later. Here, suppose the particle described in the preceding discussion has an initial speed of 5 meters per second at point A. What is its speed at point B? So this is a conservation of mechanical energy. Mechanical energies are all of our kinetic and potential energies. So if we look at this one, we have kinetic energy initial plus potential energy initial, electrical. So that's why I put a little sub E there. And then kinetic energy final and potential energy final. After that, I just substituted in the equations for each of those, 1/2 mv squared, and then Q times V for the potential energy moving the charge through a voltage. And then that's initial equals final, which is A to B, so all the sub A's to the sub B's. And then I solved it for its speed at location B. At that point, it's just a matter of plugging this in. I did not type this into a calculator, but you are more than welcome to type it into a calculator and get your answer. But just solve it for B. It's just algebra at that point. So that one's purely conservation of energy. Any questions on that one? You don't have to write this all down. It's all in the notes. But you keep writing. It's okay. And I made the video where I explained all this very quickly. But rewind it and listen to it over and over again. Pause and think. What is it he says on there? Pause and ponder. You typing it in, Michael?
Yeah, I just want to see if you're right.
Oh, thanks. 10,600 plus, what is that? Maybe 40. 350. Is it somewhere in the teens?
I got 7.
Oh, 7.8. All right, low. I was thinking that down in the lower teens, but okay. Lower than that even. All right, next. Suppose the charge in example 20-1 is released from rest at the positive plate and it reaches the negative plate with a speed of 3.4 meters per second. What are A, the mass of the charge, and B, its final kinetic energy? Okay, so again, this is conservation of energy again, conservation of mechanical energy since we're having no heat loss here. So we're starting off this time though with the, oops, I thought I had this on. We're starting off this time with the initial kinetic energy being 0. So that goes to 0. And it's just a matter of then solving for the mass since they tell us the final speed and they tell us all that stuff about it. And they tell us its charge. So I then just take this, solve it for mass, plug my numbers in. That time I did plug those ones in because I knew I was going to need it in the next part. And then the next part says, what is its final kinetic energy? And that's just doing 1/2 mv squared of the final speed. So again, don't overthink it. Just do it, right? Any questions on this one? I mean, there's not a lot of explaining to do, I don't think, on these problems. They shouldn't be too bad. The biggest problems usually are being very careful with what sign everything should be. And I gotta tell you, sometimes I get a little turned around on those and I have to stop and say, wait a second. This should be this and this should be this, and I'm moving this here, so this should be this kind of a voltage change. And am I looking at, wait, did I just calculate the work done by the field or the work done against the field by something else, or which work did I just, so it can be a bit to juggle. Here, a charge of 4.11 times 10 to the negative ninth coulombs is placed at the origin, and a second charge of 2 times that, 2 cubed, is placed on the x-axis at the location x equals 1 meter. Find the electric potential midway between the two charges. So I'm just going to calculate the electric potential due to each one at half a meter away from it. So I start off up here. The electric potential due to the just regular old Q is just KQ over R. K is 8.99 times 10 to the ninth, and then Newton meter squared per Coulomb squared, and then times that. And anyway, I get 73.9. So that's from that positive one. So if I was moving in from infinity, I would be going against the electric field there, and therefore I would get in positive. I would be increasing my voltage as I move towards that spot, right? Y'all see what I'm saying by that? Because this is our positive charge, right? And so it has the field pointed outward like this, all the way on out forever. And so if I start moving in closer to it, I'm going against the field, and that's an increase in voltage. So that's a positive voltage right there. If we look at the other one, it is a negative charge, which means the electric fields are pointed into it, which means as I move closer to it, I'm moving in the direction of the electric field coming from it. That's a drop in potential then, right?
Professor Almond,
Yeah.
could you please explain like just the VQ and KQ part? I know there's an equation with the KQ 0.
That's the potential, that's the voltage due to a single point charge. That was back here.
The 20-3, yeah.
Where was it?
20-3.
Okay. So I'm not sure what else you want me to say about it. Yeah, this.
So the K is just the potential part?
The K there is the Coulomb constant.
Okay.
And it's equal to, K is equal to 1 over 4 pi epsilon naught, the permittivity space.
Thank you.
K is. Yep. Different than the kappa K that's over here, which I always used as a kappa. But I tell you, they're just in the book, it looks like it's just a K and not a kappa. The kappas are usually kind of curly-ish, you know, like instead of a K, it's like a kappa. I don't know, but I don't know. It kept looking like a K to me. Maybe it is a little curly there, but then it's like a K right here, but it looks kind of curvy-ish there, but still not exactly like what I usually see kappas look like. Anyway, so I wasn't sure if the book was calling it capital K or kappa. It's usually in the times I've done it before, it was kappa. So anyway, then we come down here and do it for the negative 2Q one right here. So same thing, except now it's negative Q and also we're coming toward it. So it's going to be a negative potential there. And you go through and calculate and you're going to get twice what the other one was, but negative. And so then the voltage total there, very simple, just add the two numbers together. That's the beauty of the voltage part, is you just add them up and you're done. So that's all I did was add those two together. 73.9 minus the 147.8, that's negative 73.9. That's what the voltage would be at that location. Yep. Why? No, it's just superposition. Right? Like if I dug a 5-foot hole and then I threw 2 feet of dirt in it, I'd have a 3-foot hole, right? Same thing here. If I have like a 5-foot potential hole and a 2-foot hill of a potential and I combine them together, I'm gonna get a 3-foot hole of a potential, right? It's like filling in a hole, or you know what I mean? It's just purely just superposition there. For the next part, it asks, the electric potential vanishes at some point between the charges. So basically find where that is. So if you look at this here, I said, okay, I'm just going to call the distance that it goes to 0 away from the Q charge as R. And I didn't draw this in the very right place. I should actually put it over here on this side. It should have been closer to the smaller charge. I don't know. I just wasn't thinking. I just drew it real quick. And then, of course, its distance from the larger charge is 1 minus r, because the whole distance between them is 1, right? So x plus 1, or r plus 1 minus r is just 1. And that's the whole distance between them. So I come down here. I do the sum of their voltages equals 0. So I do the voltage due to a point charge, kq over r, plus k times negative 2q over 1 minus r. And I set that equal to 0. So that means that kq over r equals k 2q over r, or over 1 minus r. Cancel out the stuff that's the same. Started writing kind of small here. Cancel out the k's and the q's that are the same. So you end up with 1 over r equals 2 over 1 minus r. Cross multiply or whatever you want to do there. 1 minus r equals 2r, 1 equals 3r, r equals 1/3. So it's 1/3 of a meter. Yes. Why? Yes. Yes. They don't make a uniform electric field between them. And even if they did, the voltage would be different at every point anyway. I mean, even if we have a uniform slant down a hill, the height is different at everywhere along there. Even if we have a uniform field, that voltage is different as we move through it. I don't know, it just was always a lot easier for me to think of voltage as telling me how steep of a slant I had. Negative voltage drops were going downhill, positive voltage drops were going uphill. And then just negative charges like to go uphill for some reason. Okay, now everybody's leaving 5 minutes early. Is the test next or something like that? Is that what's going on here? Okay, then this one, we had 2 charges held in place, plus D, negative D, and a third charge is released from rest there. Find the electric potential due to the first 2 charges of the initial location of the third charge. So for there, same sort of thing, except it's a different distance away from each one of them. And I don't care about the third charge. I'm just finding the potential at the location of the third charge. So if you'll notice in part A, that 3Q, that third charge, is not in any of that calculation. It's just KQ over R plus, in which case R is square root of 2 times D, and then 2 times that for the 2Q one. They're both positive, so they're gonna add up and give a larger potential there. And then part B, the initial potential energy of the third charge. Well, we just found the voltage at that location. And so potential energy is voltage times charge. We're going to put a 3Q charge there. So it's just V times 3Q, whatever the voltage is between them, right? Which we just found up there was 3 over root 2. So it's 3 over root 2 K over D times 3Q. Voltage times charge. So we're doing a lot of the same calculations over and over again, aren't we? So anyway, part C asks, what is the kinetic energy of the third charge when it's moved infinitely far away? So this is a conservation of mechanical energy again. We're putting it there at rest, so we have no initial kinetic energy. We only have initial potential energy, which we just found in part B. When it's infinitely far away, our potential drops to 0, and therefore our potential energy drops to 0. Right? If 2 things are infinitely far away, they can't really push on each other anymore. And so our initial potential energy just equals our final kinetic energy. So all I did was rewrite what the potential energy was, because that's how much kinetic energy we'll get out of it. That makes sense? Okay. Any questions on this one? You struggle following what? Oh, I can slow down. I'm just trying to get through all of them, or as many of them as I can. You want me to start working them out?
Part of the problem with the actual exam is figuring out how to set up the actual problem, figure out like, oh, this.
That's what I was trying to explain. Am I not doing a good job? Sorry. I know we got to cram a lot in all at once, and so I can either give you less information in more detail or more information in less detail. So I thought this was a happy compromise where you're essentially getting the same information, just not having to wait on me to write it. Okay. I don't know. If you think of a better way for me to do it, I'm happy to listen. We don't have time. If I do all the writing and stuff, it just takes so long. And I got aggravated that time when I tried several times to write it out and it kept not recording my voice and I got so.
You also do a bunch of math tricks and like rearrange it. And so like I can't like automatically see like what equation that was to start with before you rearrange it. And it's like right to your original.
I'm gonna pause